Scholars, we ended chapter 2 with an expression that we could use to find the slope of a curve at a point. And we said that that slope was the same as the slope of the tangent line to the curve. And at the very end of some of those examples, instead of using a number for a, we just left a in the formula, and we found an expression we could plug in any x value to find the slope anywhere. So it turns out that's the whole first semester of calculus. We learned limits so that we could do this. We're about to talk about slope of a function for the whole rest of first semester. We have a name for a function that tells us the slope of a curve at any point. The name we use is derivative. So a function that gives the slope of another function, f of x, at any x value is called the derivative of f. So this is what we write. This is a formal definition for the derivative. There's a place for this on your 19 facts paper, and there's a place for you to write this into the box at the top of your notes paper. I'm expecting you write this definition, and you have to know it by heart. So the derivative of f is the derivative of f with respect to x, specifically, is the limit as h approaches 0 of f of x plus h minus f of x all over h. So you can see the similarity to the expression we had for slope of a curve. So just instead of having an a in there, we're going to let a vary by just keeping the name x. So the result is called the derivative. So that notation you saw, the f with the little apostrophe, we read that f prime of x, and that's a notation for the derivative. You see in your paper there's a place for you to write in a bunch of different ways that we notate the derivative. So might like to make a list and practice saying them. So f prime of x, if you wanted to be very formal, you could say the derivative of f with respect to x. Another notation for the exact same expression, the derivative of f, is this one. It looks like a fraction. It's not really a fraction. We say df dx. Or again, you can read that the derivative of f with respect to x. You might use a y instead, so you could say dy dx, or the derivative of y with respect to x. You can also say y prime, so y prime. These are all notations for the derivative of a function. So this is very long, but it introduces an important idea that I want us to make sure we catch. This says d dx of f of x, so the derivative of f of x. And just notice here, d dx. d dx, this part that I circled, it doesn't mean the derivative, it means take the derivative of the thing that comes after. So d dx means look at whatever comes next, in this case f of x, and find me its derivative. So d dx, the thing I circled in orange, is an operator, but df dx or dy dx, they're an actual name for a derivative. So one is an operator, one is the name. We'll get lots of practice using both. Okay, so we can talk lots more about where this notation comes from. Just notice that that little dx that you saw in the denominator does not mean d times x. It actually kind of means the same thing that it meant when we used delta y divided by delta x to find the slope. So delta y and delta x, they're very small changes in y and x. dx means a change so small that it's essentially 0. So that's the difference between slope that we've done before and moving on to calculus. Now we're going to let that change in y become so small, that change in x becomes so small that we can't even use the little triangle operator to mean delta. We needed a new name for it. So the guys who invented calculus chose this letter D. And just to add on to that, there is nothing about dy dx when I write it in that notation that means fraction or means divide, except in the sense that its origin as a notation came from that idea of change in y over change in x from computing slope. But now, once we let the change in x get so small it's essentially 0, we don't really think of that as division anymore. And then this, to repeat what I said before, this notation, d dx, that's an operator. That's like sine of, or natural log of, or square root of. It's not a name for a function, so it's not something that you could multiply by some other value. That means it's an operator. It means take the derivative of the thing that comes after. All right, so it's time to start to see if we recognize any patterns when we use that formal definition for the derivative. See if we can start to develop some shortcuts. So here's a function. F of x is 3x plus 2. Maybe you recognize this as a linear function. If you recognize this as a linear function, and you know derivative means the same thing as slope, can you tell what the slope of this function is? Well, if you recognize it in slope-intercept form, then we can tell the slope is going to be 3. But let's use that formal definition of the derivative, make sure we come up with the same result. So to find the derivative of f, which I'm going to call f prime of x, I need to take the limit. Oh my goodness, I can see that my subtraction signs have gone missing. So you might fill those in if you were writing some important notes. That's a subtraction sign. This is... Okay, so I'm going to fill them in as I go, make sure I don't miss a distribution. So I need the limit as h approaches 0 of f of x plus h minus f of x. So I'm going to take x plus h and replace x in my rule with it. So that's going to be 3 times x plus h plus 2. And I'm going to subtract what I get, I'm here, when I just copy the rule over f of x. In this case is 3x plus 2. I'm going to make 100% certain that I distribute the subtraction. So that's me distributing that subtraction sign. I get 3x plus 3h plus 2 minus 3x minus 2. And what's going to cancel out here? I see a 3x minus 3x. I see a plus 2 minus 2. And I'm going to end up with 3h over h. But what is the limit as h approaches 0 of 3h over h? F prime of x equals 3. So we did get the same result. We knew the slope was supposed to be 3 because that happened to be a linear function. We know linear functions have constant slope. So we just used that formal definition of derivative and got the same result. Okay, I noticed that once again my subtraction signs have gone missing, so I'm going to be filling them in as I go. I have a new function, 1 over x, and I've been asked to find the derivative. So the derivative, my notation is f prime of x. This requires a limit expression. It's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So if I replace x with x plus h, I'm going to have 1 over x plus h. That's where I got this expression. Put little dots there as I talk. Minus f of x, so 1 over x. I could try to replace x with 0, or sorry, h with 0, but I'm going to have a divide by 0 problem. So I'll continue with some of those techniques I learned back in chapter 2. So in this case, I'm going to get a common denominator. My common denominator for numerator and denominator is x times x plus h. Oh, I'm going to move the slide, but it's going to move my subtraction signs. Oh, that's horrible. All right, so I put some of them back in there. So I'm here. And then I decided I needed a common denominator. So common denominator, x times the quantity x plus h. And when I do that, I have to make sure that once I have the same denominator in my numerator, I'm going to have to make sure that I distribute that subtraction. So I showed that by using these parentheses here. So it's going to be x minus h. I'm going to come to the top of the next column. So that simplifies to negative h. I can rewrite this using multiplication by the reciprocal. And what's going to cancel out? Oh my gosh, even my negatives are missing. I swear they're in my original slide. Something about converting it to PDF. So once these guys cancel, this h will cancel with this h. I'll be left with a negative 1 in the numerator. It's finally safe to replace h with 0. I'm going to get negative 1 over x squared. So f prime of x is I could even put this label in f prime of x is negative 1 over x squared if f of x is 1 over x.